Okay, so what I want to show you first is just some theoretical understanding of this chapter, which is analysis of categorical variables. So far, we've been working only with predicting a numerical variable. Okay, correlation regression had a numerical predictor and also a numerical outcome, right? So we're predicting the outcome. So in correlation and regression, the outcome was a numerical variable. Also in the t-test and ANOVA, right? In the difference of means, we had to predict a numerical variable. So the predictor was a categorical variable with 2 groups for the t-test and 3 or more groups for the ANOVA. But still, the outcome to be predicted was a numerical variable. Now we move on to predicting categorical variables that have only groups, right? So normally we would go on and do frequency tables, but with frequency we can just analyze, we can just describe. We cannot really test the significance of the dependence or independence of these variables. So how do we go about this? What is the association between categorical variables? So categorical variables are nominal and ordinal variables, as you know. So we're going to talk about first measures of association and then the chi-square test. So what are the measures of association for categorical variables? I think we talked about this in CRJ 715, right? So there were measures of association that we measure, the relationship between categorical variables. And also we move on to the testing, which is generally the Pearson chi-square. And Pearson is a name that you find everywhere, right? In correlation, Pearson correlation coefficient. Now we see Pearson chi-square value and test. Okay, so I just want to make sure to maximize this, and then I want to show you lambda and gamma, right? So what's going on here? What are we measuring? Let's say that we're using the GSS, General Social Survey, and we're trying to look at the impact of religion on abortion attitudes, right? So we have abortion for any reason, one of the variables that's there, and we have the religion. Now, bear in mind that this is, I think, old data set, old GSS, probably 2004, because this is an old PowerPoint that I've created since when I first started teaching CRJ 716 in 2010. So probably this is either GSS 2004 or 2008. But anyway, the whole, it doesn't matter what the values are. What matters is the nuts and bolts, the workings, the inner workings of the chi-square and measures of association. So on the column, we'll have the abortion, the religion or different religion denominations. And on the row, we have the attitude about the abortion, whether they favor or oppose abortion for any reason, okay? And these are the numbers that we have, right? So we have 68 Protestants that favor abortion for any reason and 76 that don't favor. Now, if you look across the row, you have a total of all of those who favored abortion for any reason and those who did not favor. So 167 people supported abortion for any reason and 179 people opposed abortion for any reason. Now, if you don't know anything about, the categories of religion, but only knew the total of those who said yes or no, now you'd say no all the time for 346 people, And you'd be right more than wrong. Why? Because you would have only 167 errors if you said no all the time. If you said yes all the time, you'd make 179 errors, which is more than if you'd said no for every single one of them. I don't know how many of you have watched the chi-square video that I put out there. I explained the theory behind Lambda with like 10 people. And what would you guess if you don't know anything, or if you know at least one thing? So anyway, if we'd said no for everyone, then we would make less errors. We would make only 167 errors, right? But now let's say that religion comes into play. So we know everybody's religion denomination. So if we knew each person's religion, then we would improve our guess. How? If we knew that somebody is Protestant, then we would say no every time, and we would make only 68 errors. If we knew that they are Catholics, then we would say no again every time, and we would make only 38 errors. If some person is of Jewish denomination, then we would say yes all the time, and we would make only 2 errors, and so on and so on. As you see, so now you change the way that you guess, no and yes. But before you knew about people's religion, you would not, be able to change. You would just say yes or no for every single one of them without knowing the other variable. So now, when you add all of these errors that you make 138 errors. But before you made 167 errors. So what happens is that you now reduce the number of errors you made by knowing person's religion. Okay? So there is a simple formula for lambda. Uneducated errors were the ones when you did not know religion, and there were 167, minus educated errors, which were 138, because you knew one extra thing about these people, over uneducated errors. So that now would be 0.174. 0.174, turn that into a percentage, is 17.4% of reduced error when religion is a known factor. And using that, you can guess now attitudes about abortion for any reason. So this is, I guess, pretty simple to understand. And this is lambda. And what is lambda used for? Between the variables that are nominal and nominal, or one nominal variable and the other is ordinal. Okay, it ranges from 0 to 1. 0 is no association, just like in correlation, right? And 1 is perfect association. There is no negative number here, okay, from 0 to 1, because there is no direction. You can either improve your guessing or not. Okay. And gamma is for only ordinal and ordinal independent variable and ordinal dependent variable. Now, gamma can range from -1 to +1. There is a direction there. Okay. And negative sign, of course, indicates negative association. As one variable increases, the other decreases. Okay, so they move in opposite direction. I think the way that you can go about figuring out which one to use is, are both variables ordinal? If yes, then, I'm sorry, if no first, then you ask, are both nominal? If yes, then lambda. If one nominal and one ordinal, again, it's lambda. But if both variables are ordinal, then you can use gamma. All right, so That is only to figure out which way the direction of association is and how strong that association is, if it exists, right? Because sometimes you can find a lambda of 0 and there is no improvement in guessing when you know the other variable. But now you can see whether or not these two variables are statistically associated. Now you can have a statistical association, but no improvement in error. That can happen. When you use statistical tests, you're going to use the Pearson chi-square test, okay, for categorical variable association. How is that calculated? Now, the chi-square is calculated using the expected values rather than the observed values. So what do you expect these categorical values to be when you know that the null hypothesis is true? And when should the null hypothesis be true? Let me show you how this is done. We have the same variables, religion, and abortion for any reason. Okay, so we have the same values here. These are the observed values, the values that you see in the sample, right? So you have 167 people who said yes, they support abortion for any reason. 179 people said no. And specifically because the total is 346, you have 48.3% who support and 51.7% who oppose abortion for any reason. And the null hypothesis is that there is no relationship or no association between religion and abortion for any reason. Okay? So if there is no relationship at all, then we would expect these numbers, these percentages of each religion group. So 48.3% of Protestants, 48.3% of Catholics, 48.3% of Jews, and 48.3% of none, and 48.3% of other to support abortion. And 51.7% of these totals, and these are the totals of the independent variable, to oppose abortion for any reason. How does that calculation look like? So what would you expect, right? 144 times 48.3%, or in other words, 48.3% of the total for Protestants, okay? So that would be 70. And expected for no would be 74. So imagine now you have 68 that you observed in the sample, but you should have had 70 based on the null hypothesis. Okay, what about the other? 53, 56, 5, and 5. Okay, so now we have to look at the difference. What is the difference between observed and expected? Because the bigger the difference, the bigger the idea that these two are associated with each other, the bigger the dependence on each other. Okay, so let's calculate that. So the difference between observed and expected, okay, is -2 and 2, 15 and -15, and so on. So we should not be surprised that these are equal, just with different signs. So if you add them up, they will cancel each other out, because these are differences, just like when we did the correlation and regression, right? When we calculated the R, Pearson correlation coefficient R, we got the difference, but when you add all the differences, they cancel each other out. They're 0. So what do we do in this case, statistically, mathematically? We square them, because when you square them, then you have no chance of having a total of 0. And you can't do anything with 0, right? So now you square all of these differences, okay? And then you divide by the expected value. So square this, right? and divide by the expected. Square this other one, right? And divide by the expected. And when you do that, you add all of them. So when you add all of these, then you get the chi-square value. This is not the p-value. This is just the chi-square value. Okay? So when you have this value, right, you go to a chi-square distribution table and you look at the value for the alpha level, normally 0.05 or 5% significance level. And then you see that if this value here is more extreme than the one that you find in that chi-square distribution table, then you reject the null hypothesis. If it's not as extreme, then it falls in the non-rejection reason, so you don't reject the null hypothesis. Okay, so what happens with 20.55? It's a little bit large, on the large side, actually. So you look at also the degrees of freedom, and the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. We had 2 rows, minus 1 is 1, 5 columns, minus 1, 4, so degrees of freedom is 4. This is, on the right side, what you see in the distribution table, with degrees of freedom 4, okay, with p-value 0.05, you have a value of 9.49, okay? But even if you had a p-value of 0.001, which is very rare, right? You still have a larger or more extreme value that your sample produced than the one that you found in the critical region. So since this is more extreme than the chi-square critical value, then you reject the null hypothesis. But SPSS does this by default. It gives you a p-value, so you don't have to do all of these things, but it's just to show you how the classical approach in statistics is done, rather than the statistical approach through SPSS or any other statistical software. So what happens here now? Oh, this is a chi-square formula. Observed minus expected squared over expected, get the sum, and then you get the chi-square value. Again, this is done if you have a pen and a paper, but if we have SPSS, it's easier. So what are the assumptions? This is a hypothesis of independence of groups or variables. So assumptions are 2 variables are categorical, either nominal or ordinal, or one nominal and the other ordinal. Sample is randomly selected, of course. We already have established that. We assume that the population from which the sample is selected is normally distributed, and the sample size must be large enough so that the expected count in each cell is greater than 5. So it depends, right? If you have 5 columns and 2 rows, how many cells are you going to have? 10, right? So if you have 10 cells, each cell should be equal or more or greater than 5. So 10 cells, you should have at least 50 sample size. Even more than 50, because some samples might have 7. I'm sorry, some cells might have 7, some cells might have 10, and the other 2 will have 2 or 3. So the bigger the sample, the better it is to get a more accurate chi-square value. So when assumptions are not met, we must conduct non-parametric tests. Chi-square is also a very robust test. You know, it's in the family of non-parametric tests as well. But there is no time in this class to get to those non-parametric, to other non-parametric testing. Okay, so this is it. This is what you know, the theoretical of understanding of cross tabulations and chi-square is, okay, and the measures of association. But what about in practice? Let me show you. Do you have any questions, first of all?
So I'm all good.
Okay. I'm not seeing anybody that wants to join the room. Usually I get a notification. So it's only you three still. So anyway, if you have any questions, just interrupt me and say I have a question. We can answer that. So let's go to GSS 2018 data set. Okay, this is the full data set that I've gotten from General Social Survey. So this has 1,065 variables. Okay, and let's see how many observations do we have. I think 2,348 observations. Okay. We have the variable view, okay, and we have the variable name, the label, which is the longer name, the values, the measure. Sometimes the measure is incorrect here because they haven't had, probably the time, or they didn't think that it's important to put all the correct measurements here. So sometimes as I go and I look at the variable and I want to, use it for some tests, I change it, right? So I can change from nominal to ordinal or scale. Scale is interval or ratio. So I do that manually. All right. You probably are familiar with GSS 2018, or maybe GSS 2018 revised data set, right? Do you have any, I don't know, are you interested in to look at any association between two categorical variables? If you don't, I have some, but if you are, we can do your hypothesis. Okay. Well, if you have any hypothesis, tell me later. Let's move on with my own hypothesis. So I'm interested to look at the association between whether somebody who was born in the United States or not have different opinions on capital punishment. So we'll stay within the criminal justice field. I don't know. Maybe those who are born here have a different opinion than those who are not born here. It depends, because somebody might be born, in another country and came here when they were like 1 year old or 2 or 3. So it doesn't really make any difference. But since we don't have that intricacy level of the data, then we'll just assume that those who are born outside of the United States have sort of different opinions on many things. But one of those things is, capital punishment. Right now, I have no idea what's going on, and that reflects the null hypothesis. The null hypothesis is that there is no association between whether somebody is born in the United States or not and their opinion in capital punishment, whether they favor or oppose it. And we're going to test that at the 0.05 alpha level. The alternative hypothesis is also a two-tailed hypothesis, because I have no idea how the opinion differs, or I have no I don't know, literature or research that says different, right? And that's why it's going to be that there is a significant association between whether somebody is born in this country and their opinion in about capital punishment. So we're trying now to figure out or predict somebody's opinion on capital punishment, whether they oppose or favor capital punishment. And you see, so we're predicting a categorical variable. Either is going to be 1 or 2. And that is cap pun. where is it? Right here. Cap fun. Favor or oppose death penalty for murder. Okay. So when we go to values, we see 1 is favor and 2 is oppose. Okay. So there are 2 categories here. Don't worry about the 0, 8, and 9 generally are missing cases. Those who said it's inapplicable, or maybe the researcher did not ask this question. Those who said don't know, those who say not available. All right. So usually when you work with SPSS data set, it's always best to put the 0, 8, and 9, or if there are more than 9 categories, then you put 88, 99. Okay, so that they don't conflict. They don't look like parts of or categories of the variable, but they depict these missing values. Okay, so we're going to sort of predict these people's opinion based on whether or not they're born in this country. All right, so we go to analyze. Can you tell me next? I forgot. How do we go to crosstabs?
Descriptives.
Okay. Oh yeah, descriptives. Okay, descriptives, and here we go to crosstabs, right?
Yeah.
All right. Now, one thing that you have to keep in mind, this rows and columns. SPSS and statisticians behind this powerful software intentionally did not put independent or dependent or factor or predictor or outcome, because it depends on you. It depends on the user. You can put the independent variable, the one that predicts the other, in the columns, or you can put in the rows. But then you have to decide which percentages you're going to get. And I'm going to show you. So I generally like to put the independent variable, the predictor, in the columns. Okay. So I'm going to put cap fun. No, I'm sorry, born, because that is the one that I think is the predictor. Born in the columns, and cap fun in the rows. Okay, so in the columns, you will have the categories of born, yes or no, whether they were born in this country, yes or no, right? And cap fun, whether they favor or oppose capital punishment. So I'm going to go to cells, and I'm going to ask for column percentages, because I want column percentages. And what does that mean? It is the percentage of each of the groups of the column variable, the groups born in this country, yes or no, to sum or total 100%. Okay, not across the row. That is the total of 100%. I want the column percentage to be 100%. And I'm not going to get expected right now. I'm going to get it later. But so far, I just want to show you one part of the crosstabs. And that part is very important, just to look at and analyze the cross-tabulation. So I'm going to click continue. And I'm not going to go to statistics. We're going to do that later. And I'm going to click OK. 2 tables here. Case processing, valid cases, missing cases. All right, so we have about 156 missing cases and about 2192 valid cases. You don't have to report this in your assignment. It doesn't really matter. Why? Because this valid cases is going to be here as the total in the most important table, which is this. That's the crosstab. So what's going on here? We have the column variable was respondent born in this country, yes or no. So 1,916 people were born in this country, the one that, from the sample 2192, and 276 that were not born in this country. Okay. Now, within the row, we have the favor or oppose death penalty for murder. So 1,384 favored, death penalty for murder, and 808 people opposed. So these totals, right, could be done in another way. If you remember, if we go to frequencies, right, we can get those numbers very quickly. Born and cap pun. Okay. Let me create APA style tables here. I don't need this. Okay. So the way I did it this way is so that I can have everything in one screen. All right. So, okay, these are not going to be the same because missing cases are going to skew these numbers just a little bit. Okay. But don't worry too much about that. So, for example, those who favor or oppose death penalty for murder, we have those who favor 1385. We have here 1384. Okay, because one was missing somehow. And those who oppose 808. Here, whether the person was born in this country, we have 2045, but in the cross tabulation we have 1916, and 302 were not born, but 286 in the cross tabulation. So cross tabulation takes away one case that might be in one variable, but it's not in the other. Okay, so I just wanted to show you that. But the frequency does not tell you how many of these 2,045 people who are born in this country favored or opposed death penalty. No, only the cross tabulation tells you that. So among those who are born in this country, 1,245 favor and 671 oppose. Okay, so let me delete this and go back to this table. By the way, I can't make it bigger for some reason. So you're going to have to, I don't know, make your screen bigger, I guess. So what is going on here? Well, I requested column percentages. So when you request column percentages, this number and this number will be, I mean, these percentages will be 100%. So among those who said who were born in this country, 65% favor and 35% oppose death penalty. Of those who are not born in this country, 50 and 50. So they're split in half virtually. Okay, less than 1%. But that is not how you compare. Okay, you compare across the row, even though total percentages are in the column. And actually, because the percentages are in the column, you are able to now look at the difference of percentages across the row. So this difference turns out to be, in statistics, a value called epsilon. Okay, so let's look at this epsilon. 65 minus 50, okay, it's almost 15%, 14.6%. So that is actually that rather large difference. The same thing is here, 14.6%. But you can, for the epsilon, you can look at only one, either row, favor or oppose, and you see the same number. So if this difference here was very, very small, maybe 1 or 2%, then you would say that, okay, this doesn't seem to have such a big effect. Whether the person is born in the country does not really affect how their opinion on death penalty is. But in this case, it does. In my opinion, even though I don't know the chi-square still, I can say that this difference is significant. Almost 15% difference in an opinion is rather large. Okay, so that's how you look at and um, you know, analyze or interpret the percentages and the cross tabulation. This is one of the easiest because it has only two groups. I mean, both variables have only two groups. But if you have more than two groups, then you have to look at, the epsilon between the smallest percentage and the largest percentage and make your interpretation. Okay, let's now see the measure of association. Is this association rather significant in terms of the measurement? And because these two are nominal variables, we're going to look at lambda, okay, and also we're going to look at the chi-square. We're going to go back to analyze descriptive statistics, crosstabs. Okay, born and kept pun is here. Cells. I'm just going to add expected this time, just to show you if that difference between observed and expected is also large. Continue. In statistics, I'm going to get chi-square, lambda, and I'll get a phi and Kramer's V to look at, not only the significance also, but the measure and the strength, the strength of the association. And lambda, so I talked about lambda, but do not confuse lambda with the strength of the association, actually. Lambda is only a measure of improvement in error guessing. Okay, how much we would improve our guessing if we knew the other variable. Okay, let's continue. Click OK. And now I'm going to delete the cases. So expected count under the null hypothesis, we would expect 1,210 people to favor death penalty if they were born in this country. But actually, the observed, the real value is larger than that. We would expect fewer people to oppose, but I'm sorry, we would expect more people to oppose death penalty, but we have fewer. And for those who were not born in this country, we would expect more people to favor, but the reality is that fewer people favor it. All right. So what is this difference? It's about 35 here. Okay, so that's rather big difference, right? Because as you know, you have to square that difference and divide by the expected. So that's a big difference, and that is shown in the value Pearson chi-square. You look at the first row. The value is rather large with 1 degrees of freedom. Why is 1 degrees of freedom? Because there are two groups minus 1, and then two groups in this other one minus 1. So it's 1 times 1, 1 degrees of freedom. All right, the p-value is smaller than 0.001. That is a p-value that is smaller than 0.05 that we actually said that is going to be our significance level in the null hypothesis. Therefore, we reject the null hypothesis. When we reject the null hypothesis, we state that we will accept the alternative hypothesis and say that we have sufficient evidence to say that these two variables are dependent on each other. So knowing, whether somebody is born in this country can significantly predict whether or not they favor or oppose death penalty. Let's move on to the lambda. Lambda actually, it's kind of strange. And I said that whether the, relationship is significant statistically, it does not really mean that lambda is going to be greater than 0. It does not tell us that knowing, what was it? Whether the person was born in this country is going to improve our guessing that that person favors or opposes death penalty. No. However, And when we go to the nominal by nominal symmetric measures, then we see that there is about 10% association strength. 0.1 is rather weak association, even though statistically this is a significant association. One thing about phi and Kramer's V, this is just theoretical. When you have two variables with two groups each, right, phi and Kramer's V will be the same value. But if you have a variable that has more than two groups, or both variables have more than two groups, then Kramer's V is the best measure of strength. Phi is only 2 by 2. Okay. In this case, it's the same. So it's a practically weak association, even though statistically is very strong. Okay, so that's all we can say here about these two. Here's another one. What about the idea that being born in this country also affects the opinion that one has on the confidence in United States court system? Let's look at that. So we go to analyze again, descriptive statistics, crosstabs, and now replace CAPON with confidence in courts. So it should be Concord. It's right here, Concord. This time we're going to ask for everything. I did those step by step so that I can show you, that you first need to understand the table, okay, and need to interpret those percentages rather than straight go to the chi-square and say, oh, okay, this is the p-value is smaller than 0.05, case closed, reject, null, accept, alternative, and that's it. No, that is not how one in this level, is going to have to interpret things. You have to dig deeper, maybe think outside the box, think of something that these numbers are telling you, and then do a more elaborate interpretation of what you're seeing. Okay, because even though we're trying to teach you guys the best teacher is the job. So if you're doing this for your job, then you're definitely going to have to be smarter and better than if this was not for a paying job. So let's look at this. Was respondent born in this country? Yes or no? Again, now confidence in court and legal system is a variable with more than two groups, and this is actually an ordinal variable. Let me see if I have changed this. Concord. Oh, no, I haven't changed it. Let's change it to ordinal, and let me do it again. Crosstabs, cells, expected column, fine. And statistics, instead of phi and Kramer's V and lambda, we're going to go to ordinal now. Or should I? Which one of these should I do? Just say one. You have a 50% chance of reducing your error. Or guessing wrong.
Okay. Lambda.
Lambda. Why?
Oh, because there is an ordinal and a nominal.
That's very good. That was a trick thing, just to see if you're paying attention. So ordinal, we go to ordinal only when both variables are ordinal, okay? When both are ordinal. We're going to continue with chi-square, phi and Kramer's V, lambda. Let's do continue. Cells expected in column, continue, click OK, and that's what we have. So let's look at these differences here. Among those who were born in this country, right? 3% have complete confidence in courts and legal system. 50% some confidence, 24% very little confidence, and 7.5% no confidence at all. This is crazy. 15% have a great deal of confidence. So only 3% have complete confidence compared to 12.2% who have complete confidence among those who are not born in this country. So we would see some difference here, right? What was this difference called?
Epsilon.
Epsilon, right? Epsilon. So we do have about 9%, right? 9.2% difference in those who have complete confidence between those who were born in this country and those who were not born in this country. Okay. What about here? 9.2%. Here we have, in some confidence, we have about 4.1%. And very little confidence, there is probably the highest percentage, right? Almost, no, it's more than 11%, 11.2%. And then we do have about 4% epsilon here. So the biggest difference is among those who have very little confidence, and those who are born in this country are about 11% more that have very little confidence in courts and legal system than those who are not born in this country. Okay. Now, somebody who really wants to research this even deeper can go and figure out some more predictors, because only the idea that somebody is born in this country or not is not the complete, reason why the confidence in courts and legal system is different, right? There might be some other stuff, maybe personal experience, maybe, I don't know, a lot of different things that one can think of. But as we can see here, I can confidently say that just by eyeballing this, that this difference is significant. Okay, I'm going to go to the chi-square test. Oh, it's right here, and I didn't even look at it. But look at this value. Oh, and also the expected counts. Okay, we would expect a lot more people born in this country to have complete confidence, but only 30 have. So we would expect about 43 people, only 30 are found in the sample. And we would expect fewer people, to have complete confidence from those who are not born in this country, but we have a lot more. Okay, and the same thing can be said in the other rows. Is this relationship significant, statistically significant? Yes, it is. P-value is smaller than 0.001. Therefore, we again reject the null hypothesis and accept the alternative hypothesis, and that shows sufficient evidence of dependence, not independence. They are not independent of each other. They depend on each other. So knowing that somebody was born in this country or not can yield statistically significant results in terms of their opinion and confidence in courts and legal system in the United States. Okay, can we improve the error just by knowing if somebody is born in the country or not? Okay, with Lambda, we can't. It's 0. All right, so we can't say that knowing that somebody was born in the country or not is going to improve our guessing in terms of how their opinion or confidence in legal system is. It's 0. What about the strength of this association, the practical strength. All right, so phi and Kramer's V is the same again. Okay, so even though one variable had more than two groups, still Kramer's V shows the same as phi. Okay, so this is not completely weak relationship. It's a moderate to medium relationship. So it kind of shows that there is some strength to this relationship. And also we can see that from the difference from the epsilon. So basically that's all you can say, analyzing cross tabulation and then interpreting all these tests. I have one more test that I want to make, and that has to do somehow with the discussion board question, one of the questions. And I want to find out, even though this is not exactly the question in the discussion board, the variables are the same, even though I ask you to do it in a different order, but I'm going to do this. I want to figure out whether there is a relationship between gender and fear to walk at night in their neighborhood, right? So I'm going to go to Analyze, Descriptive Statistics, Crosstabs. I'm going to find gender. I think this is called sex. It should be where the... Okay, I think it's in here. Okay, sex. So that's in the column, right? Because we think that that's the predictor. And fear. Fear. Okay. In cells, we're going to get the column again, expected. Statistics, the same things here. And then click OK. Now you can tell me, just by looking at this, well, I can't really separate it because, okay, yeah, just looking at the cross tabulation here. Look at the expected counts. Look at the column percentages. Okay. Do you think that you have a statistically significant relationship? Do you think that gender is a good predictor of fear to walk at night in neighborhood? The first thing you look at is how many males and females are there. 700 males and 867 females in the sample. How many are afraid and how many are not? More people are not afraid. Okay, by 2 to 1. I think somebody was talking. Yeah, go ahead, please. You were saying that there is or there is no relationship? Okay. What is the epsilon here? Among those who are afraid, right? How many are females? 42.7. And how many are males? 21.6. So it seems like it's double the percentage of males. And of those who are not afraid, 78.4% are male and 57.3% are female. So here is about 21% difference, and the same thing here, about 21% difference, right? So again, with the epsilon, you can just look at one of the rows and the other, because the percentages are down the column, right? If the total is 100% here, 42.7% females who are afraid and 57.3% who are not afraid. make 100%, right? The comparison should be made across the row again. So I can see here that respondent sex is a good predictor of whether somebody is or is not afraid to walk at night in the neighborhood. Okay. What does the chi-square test tell us? The same thing. Also, the expected counts. We would expect more males to be afraid, but in actuality, fewer are. We'd expect fewer females to be afraid, but in actuality, more responded that they were afraid. You see? So that difference is squared and divided by the expected count. And then plus difference divided by this expected count plus the difference divided by this expected count and that comes to 77.77. With 1 degree of freedom, this is the p-value. Reject the null hypothesis, accept the alternative, and then you write what the alternative is and how you have sufficient evidence to accept the alternative hypothesis. Okay, now knowing whether a person is male or female, does it help you to better predict whether they are afraid or not? So that's one question. The other question is, knowing whether somebody is afraid or not, can you predict whether that person is a male or female? And if you can, by what percentage you can improve your guessing error? Okay, in relation to the first question, knowing somebody's gender, it doesn't help you predict whether they're afraid or not. But knowing whether somebody is afraid or not to walk at home in the neighborhood at night, you can improve your error in guessing their gender by 7.4%. Again, if you do think of any other questions, just send me an email. All right. Or if you have any question about the assignment discussion board, okay, send me an email saying that this is what I have. Is that okay or not? Okay, and I'll give you some pointers. All right, so make sure you go to Blackboard and over here, right? And then just take this survey. It's only 3 questions that ask how you found your whether the textbook was helpful, all right, or whether or not you recommend it, and just write whatever you need here. If you don't find it helpful, just tell me why, or if you found it helpful, why as well. Okay, so I don't have anything else. Thanks for joining me in this session. All right, so have a great day, everyone.
Thank you.
Talk to you soon.
Thank you.